right. Good morning, everybody. Today is Friday, December 22nd, 2017, and this is Before the First Cup with Jules here on UCY.TV. Happy Friday, everyone. It is a chilly 27 degrees under a winter storm warning with about a half inch of icy little snow BBs all over the place. So where did we leave off yesterday? We titled the show DARPA, Living Foundries, BTO is in the Biological Technologies Office, Pandemics, Synthetic Biology, and Body Snatchers. And we looked at a lot of different things that DARPA had been working on, engineering organisms, and being able to flip switches and break life up into tiny components that then can be reassembled in some new format. Also, they had taken the lead in synthetic biology and trying to create life that had never been seen before on this planet, which should worry you, as this is the military-industrial complex that is working on these things. Now, of course, they can roll these all into benefit. We found out there was some debate going on, and I don't remember which group it was, but one of them was putting their foot down saying, it was one of the viral groups, because they decided now that they can begin experimentation again after a 3-year moratorium on making killer viruses more virulent. And of course, it's all in the name of keeping you safe in case this stuff mutates accidentally or on purpose in the environment. They will be able to create some sort of remedy that will be able to protect you. But also remember, it's always a double-edged sword, and our biowarfare program never ended unofficially. We have traced a lot of this back to Plum Island. We mentioned Plum Island the other day, that is now in the heart. It has been moved to the heart of Tornado Alley in Manhattan, Kansas. And they haven't quite finished that facility from what I understand yet, but it's coming. It's coming. And they have to do better biosecurity. Of course, that's something that they haven't done very well at across the board. Now we add a lot of these genetic technologies, such as CRISPR-Cas9, that has been democratized across the planet, and they have deemed it a WMD, and we should be paying attention. So we're going to take this one step further. So not only are we looking at a biological level that they can try to recreate life, but DARPA has had its hand in something else as well. As far back as at least 2007 or 2009, there was a story that came out of Popular Science, June 8th, 2009. DARPA's Programmable Matter project creates shape-shifting materials. Now, probably a year or two ago, we had started looking at some of the shape-shifting materials. There were some surprising things. I wanted to touch on that again because this fits in very well with what we were looking at yesterday with that Biological Technologies Office. Well, this is taking it even a step further. This is integrating life into living materials that can react to their environment. From tools that morph themselves structurally to suit a job, and to sentry bots that can change shape to squeeze through narrow passages, programmable matter is a far-out concept that is difficult to imagine outside of the movies, but thanks to some creative work done by scientists funded by DARPA, who else, it might actually become a reality to create materials that can be programmed to alter themselves at the molecular level into various shapes and then disassemble to form entirely new ones. Imagine universal tools that can morph to perform specific job needs. And imagine vehicles and clothes that can automatically change their shape, perhaps even at the molecular level, according to terrain or climate. There's a new report on programmable matter, which is intuitive, spanning a group of projects working toward a final goal of creating substances that can morph into objects as needed. One Harvard team, who else would it be, created self-folding origami, and we had read about that, if you remember. The origami stuff comes out of the beginnings of the robo-bees at the Weiss Institute of Biologically Inspired Engineering. We've covered them at length. And they had created sheets of these little origami robots that were flat, and then just by a little electrical pulse of some kind, it caused the joints that were 3D printed into these origami sheets to start to heat up and bend, and the robots folded themselves into the structure and then flew away or something. It's pretty crazy, or started moving around. One Harvard team created self-folding origami structures with integrated actuators and data storage that will fold themselves into different shapes. And there you have it. A team from MIT has even built tiny servo motors that can control the assembly of objects underwater or in space. Other teams have approached problems by mimicking DNA or protein synthesis and creating of objects, and the projects are only in their second stages of development. Remember, this was in 2009, ending sometime next spring, but by that time they are hoping to have a working model that can assemble into a few different solids. Once some of these ideas are realized and integrated into a working form, the possibilities are almost endless. Oh, get excited. Blurring the line between materials and mechanics, it may even result in new states of matter. Oh, great. Guys, this is like Cuckooville. I mean, I got to tell you, as I read more and more, my mind really has a hard time grasping all of the implications as to where we are headed as a society. This is very frightening. One possibility are info liquids and info solids, materials that straddle the line between solids and liquids with information encoded into their chemistry. Another possibility is the creation of robots that can shift sizes and even states of matter to squeeze through narrow passages or around obstacles, or maybe even tiny enough to get into your bloodstream. I added that one, but it's coming. Wired magazine also points out theorizing models that can mimic shapes in real time, similar to holograms. So this could allow a replica of yourself to exist and move as you do somewhere else on the other side of the world. That'll probably be some next generation in the future avatar system. Forget Autobots and Decepticons. This is the real deal. So that's DARPA. So now let's look at programmable matter. According to Wikipedia, programmable matter has the ability to change physical properties, and that would be shape, density, moduli. So that would have to be maybe modularity. I don't know. What is moduli? Is the plural of, some sort of quantum theory, sometimes referred to as scalar fields. So it can change scalar fields. Conductivity and optical properties in a programmable fashion based upon user input or autonomous sensing. Oh, yes, we gotta love autonomous sensing, little living mini computers. Programmable matter is thus linked to the concept of a material which is inherently has the ability to perform information processing. All right, so the history of programmable matter. It was originally coined in 1991 to refer to an ensemble of fine-grained computing elements arranged in space. There was a paper describing a computing substrate that is composed of fine-grained computing nodes distributed throughout space, maybe like a little bit like smart dust or nanotech, which communicates using only their nearest neighboring interactions. So that would be more like a swarm technology. And in this context, programmable matter refers to computing models similar to cellular automata and lattice gas automata. The architecture is an example of hardware realization of this model, and this function is also known as the digital referenced area in some forms of self-replicating machine science. Oh my God, are we really talking about this? In the early 1990s, there was a significant amount of work in reconfigurable modular robotics with a philosophy similar to programmable matter. As semiconductor technology, nanotechnology, and self-replicating machine technology has advanced, the use of the term programmable matter has changed to reflect the fact that it is possible to build an ensemble of elements which can be programmed to change their physical properties in reality, not just in simulation. So this is real, guys. This programmable matter has come to mean, quote, any bulk substance which can be programmed to change its physical properties, unquote. In the summer of 1998, in a discussion on artificial atoms and programmable matter, William McCarthy and G. Snyder coined the term quantum wellstone to describe this hypothetical but plausible form of programmable matter. McCarthy has used this term in his fiction. And in 2002, Seth Goldstein and Todd Morey started the Claytronics project. And I have some stuff on this Claytronics we're going to read at Carnegie Mellon University. And remember, that is the home of AI, where Barack Obama gave his lecture about how artificial intelligence was going to change society of the future, to investigate the underlying hardware and software mechanisms necessary for realizing programmable matter. In 2004, the DARPA Information Science and Technology Group examined the potential of programmable matter, and this resulted in the 2005-2006 study, Realizing Programmable Matter, which laid out a multi-year program for research and development of it. And in 2007, programmable matter was the subject of a DARPA research solicitation and a subsequent program. And I don't know what that subsequent program is. So now let's see if we can find that Claytronics, because I think that's right here. All right, Claytronics. Welcome to the Claytronics project. It is a collaborative research project in programmable matter directed by Carnegie Mellon University and Intel. And that was something that I didn't know about before, was the relationship of Intel. This project combines molecular or modular robotics, systems nanotechnology, and computer science to create a dynamic three-dimensional display of electronic information known as Claytronics. Our goal is to give tangible, interactive forms to information so that a user's senses will experience digital environments as though they are indistinguishable from reality. Ding, 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 ding. This has always been the key, to make things indistinguishable from reality and to suck you fully into the matrix. I'm telling you guys, this is where they are taking us. The next thing will be the digital AI god, and then uploading yourselves to be forever trapped in the machine. Claytronics is taking place across rapidly advancing frontiers, and this technology will help drive breathtaking advances in the design and engineering of computing and hardware systems. Creating, as part of our focuses, our two main projects are creating the basic molecular building blocks of Claytronics, known as Claytronics atoms or CTOMs, and designing and writing robust and reliable software programs that will manage the shaping of assembles of millions of catoms into dynamic three-dimensional forms. Realizing the vision of Claytronics through self-assembly of millions of C atoms in a synthetic reality will have a profound effect on the experience of the user of the electronic information. This promise of Claytronics technology has become possible because of an ever-increasing speed of computer processing predicted in Moore's Law, and this website will introduce you to the ideas that are driving Claytronics, the research team that's working to make it happen, and the hardware and software projects that enable the building of Claytronic ensembles. Development of this powerful form of information display represents a partnership between the School of Computer Sciences at Carnegie Mellon University, Intel Corporation and its Pittsburgh laboratory, and the Femto ST Institute. And as an integral part of our philosophy, the Claytronics project seeks the contributions of scholars and researchers worldwide who are dedicating their efforts to the diverse scientific and engineering studies related to the rich field of nanotechnology and computer science. I mean, guys, this is crazy. This is going to be a brand new 3D reality interfacing for computing that can morph on the fly, real time, to turn into structures. All right, so now here's a story out of ScienceDaily.com. Building, living, breathing supercomputers. The substance that provides energy to all of our cells and bodies is ATP, and that is adenosine triphosphate, and it may also be able to power the next generation of supercomputers. This discovery opens the doors to the creation of biological supercomputers that are about the size of a book. Oh no, we'll have a big library of them on the shelf. The substance that provides energy to all the cells in our body, ATP, may be able to power the next generation of supercomputers, and it opens the doors to the creation of biological supercomputers that are about the size of a book, and that is what an international team of researchers led by Professor Nicolau, the chair of the Department of Bioengineering at McGill University, believe. They have published an article on the subject earlier this week, and this was back from February of 2016. So this was about a year ago, in which they described a model of a biological computer that they have created that is able to process information very quickly and accurately using parallel networks in the same way that massive electronic supercomputers do. Oh my God. Guys, does Jabba the Hutt mean anything to you? I just can't even get over some of the stuff. And where are the ethics in this? Living supercomputers that then they're going to imbue with some sort of mentally unstable, creative artificial intelligence as they reprogram the cells with a few flashes of light. I mean, it's just insane. Except... So the only difference is that the model bio supercomputer that they have created is a whole lot smaller than current supercomputers, and it uses much less energy. It uses proteins present in all living cells to function, so we can become a power source of the future. We have managed to create a very complex network in a very small area, says Dan Nicolau. With a laugh, probably diabolical laughter. And he began working on the idea with his son, Dan Jr., more than a decade ago, and then was joined by colleagues from Germany, Sweden, and the Netherlands some 7 years ago. This started as an envelope idea after too much rum, I think. With drawings of what looked like small worms exploring mazes. Oh, well, that's not and rotting flesh. I'm sorry, guys, but this is just too much. The model bio supercomputer that Nicolau's father and son and their colleagues have created came about thanks to a combination of geometrical modeling and engineering know-how on the nanoscale. It is a first step in showing that this kind of biological supercomputer could actually work. The circuit the researchers have created looks a bit like a roadmap of a very busy and organized city as seen from a plane. And just as in a city, cars and trucks of different sizes powered by motors of different kinds navigate through channels that have been created for them, consuming fuel they need to keep moving. But in the case of the biocomputer, the city is a chip measuring about 1.5 centimeters in which channels have been etched, and instead of electrons that are propelled by an electrical charge and move around within a traditional microchip, short strings of proteins, which the researchers call biological agents, travel around the circuit in a controlled way, and their movements powered by ATP, which is the chemical that is in some ways the juice of life for everything from plants to politicians. But it is run by because it is run by biological agents, and as a result, hardly heats up at all. The model bio-supercomputer that the researchers have developed uses far less energy than standard electronic supercomputers do, making it more sustainable. So it's going to be a green solution. Traditional supercomputers use so much electricity that they heat up a lot and they need to be cooled down, often requiring their own power plant to function, and a whole bunch of air conditioners. Although the model bio supercomputer was able to very efficiently make classical complex mathematical problems by using parallel computing of the kinds used by supercomputers, the researchers recognize that there is still a lot of work ahead to move from the model that they have created to a full-scale functional computer. Now that this model exists as a way of successfully dealing with a single problem, there are going to be many others who will follow up and try to push it further using different biological agents. And it is hard to say how soon it'll be before we see a full-scale bio-supercomputer. This is nuts. One option for dealing with the larger, more complex problems may be to combine our device with conventional computers. Let's merge biology and technology to form a hybrid device. Right now, we are working on a variety of ways to push the research further. Once stuff that was part of science fiction is now just science, he says. So, all right, now let's take the next step. This is a paper published in 1981. I had found a reference to it and did a search, and I actually was surprised I found it. 1981, written by Eric Drexler, our old buddy, the father of nanotechnology out of MIT. And it is published in the Institute for Molecular Manufacturing, titled Protein Design as a Pathway to Molecular Manufacturing. We're not going to read the special thanks. All right, Molecular Engineering by K. Eric Drexler. The development of the ability to design protein molecules that will open a path to the fabrication of devices to complex atomic specifications, thus sidestepping obstacles facing conventional microtechnologies. This path will involve construction of molecular machinery able to position reactive groups to atomic precision. This could lead to great advances in computing devices and the ability to manipulate biological materials. Ding, ding, ding. And the existence of this path has implications for the present as well. This was written June 4th, 1981. In Richard Feynman's 1959 talk entitled There is Plenty of Room at the Bottom, and I actually saw Richard Feynman back at the University of Buffalo in like I'd have to say maybe 87 or 88. It's pretty interesting. I didn't realize who he was at the time. According to his talk entitled There is Plenty of Room at the Bottom, he discussed microtechnology as a frontier to be pushed back, like the frontiers of high pressure, low pressure, or high vacuum. He suggested that ordinary machines could build smaller machines that could build smaller machines, working step by step toward the molecular level, and he also suggested using particle beams to define the two-dimensional patterns. And would that be like a laser doing 3D printing? Present microtechnology, exemplified by integrated circuits, has realized some of the potential outlined by Feynman by following the same basic approach, working down to the macroscopic level, from the macroscopic level to the microscopic. Present microtechnology handles statistical populations of atoms. Hold on, I got to zoom in just a little bit. And now I have to find out where I zoomed, and then I lost my place. Populations of atoms, and as the devices shrink, the atomic graininess of matter creates irregularities and imperfections so long as atoms are handled in bulk rather than individually. Indeed, such a miniaturization of bulk processes seems unable to reach the ultimate level of microtechnology, the structure of matter, to complex atomic specifications. In this paper, I will outline a path to this goal, a general molecular engineering technology, and the existence of this path will be shown to have impact for everything from the present to the future. So how we're going to do that is with protein design. Biochemical systems exhibit a microtechnology quite different from ours. They are not built down from the macroscopic level, but up from the atomic level. Biochemical microtechnology provides a beachhead at the molecular level from which to develop new molecular systems by providing a variety of tools and devices to use and to copy. Building with these tools themselves made from atomic specifications, we can begin on the far side of the barrier facing conventional microtechnology. What can we build with these tools? Well, with gene synthesis and recombinant DNA technology. Oh, yes. We can direct the ribosomal machinery of bacteria to produce novel proteins, which can serve as components of a larger molecular structure. And that was some of the stuff we were talking about yesterday. Some of this DNA and RNA technology that DARPA was getting into to create self-healing immune systems that can react to any threat, known or unknown. Building with these tools themselves, made to atomic specifications, we can begin at the far side, and we can work on gene synthesis with the recombinant DNA technology to direct the ribosomal machinery of bacteria to produce novel proteins, which then can serve as components of larger molecular structures. One might think assembly of such components into complex systems would require a pre-existing technology able to handle molecules and assemble them structures from solution. For example, and remember DARPA was building a cellular factory as well. Hold on one second. Where was that? I think that was at one of the institutes associated with MIT and Harvard. The Broad, yes, the Broad Institute. $32 million for DNA design and manufacturing. But wait, there was a cellular factory as well. $30 million to jumpstart cellular factories. And where was this one? DARPA and their living foundries. Oh, and Ameris. That was that synthetic biology company. So anyway, at present, the design of protein systems as complex as ribosomes seems to be an awesome task, but remember that was in 1981. Not anymore there, buddy. Indeed, chemists cannot yet yield three-dimensional conformations of a natural protein from its amino acid sequence, an ability that might seem requisite to the design of new proteins. But that was the new frontier coming in medicine we had read a while back. Two considerations suggest that this obstacle is surmountable. First, the continuing improvement in protein science, and second, the difference between natural science and design engineering. But remember, they've been merged now with DARPA's BTO. Regarding the first, computer simulations of protein molecules in solution show promise, and as computer technology and chemical knowledge improve, simulations will increase in accuracy, speed, and size, and improvements promise new insight into protein behavior that they can now create on the fly and may permit the designer to modify simulated molecules and even in the real life quickly and observe their behavior directly. So now let's take a step further. 1981, let's fast forward to 2009, where we started this show. DARPA's Programmable Matter project creates shape-shifting materials, and they were tinkering with proteins. Go figure. And their goal, of course, is to create things that can mimic shapes in real time. We have Intel and Carnegie Mellon University that is also behind creating the Claytronics, or whatever it was called. Makes me think of claymation. All right, so now here I have an excerpt from a book from somebody named Skylar Tibbetts. And just for the name itself, we had to read this excerpt. It's a really cool name. I hope that is their original name. And he, she, I don't know who it is an assistant professor of design research in the Department of Architecture at MIT. It's pretty interesting. The excerpt is called Active Matter. Here's an excerpt from Active Matter. And over the past half century, we have experienced a software and hardware revolution. We are now experiencing a true materials revolution. By the way, I looked this up on Amazon. It only comes in hardcover. It was just released in September of 2017. It's like $32, which I was quite disappointed they didn't have a Kindle version. But it was nice that someone put an excerpt out there. We can now sense, compute, and actuate with materials alone, just as one could previously with software and hardware platforms, and it is becoming increasingly clear that materials are a platform for turning digital information into physical performance and functionality. If yesterday we programmed computers and machines, today we program matter itself. Well, how did active matter emerge? We go back to the history of computing with Ada Lovelace, Charles Babbage, and even the Jacquard loom as the implementation of mechanical computing for industrial production with a true material output. Or we perhaps could emphasize Turing, von Neumann, and other incredibly important figures in computing, but it seems to make more sense to start at the beginning of the quote-unquote digital age and how it relates to the physical. In 1937, Claude Shannon produced what has been described as one of the most influential master's theses of all time. I never read this one. Maybe I should look it up. In which he introduced the concept of Boolean logic for relays, digital logic eventually becoming the foundation of digital communication electronics and information theory. Since the subsequent invention of the transistor in 1947. Remember, these dates in this timeline, we realized looking at Bell Labs that a lot of this technology that we thought was much further down the timeline actually started being developed way in the early days, when we didn't even realize that they had electronic capabilities. And these are included 1937, 1947. We found out Bell Labs was even working on stuff back in the 20s and were very involved with the federal government when they got taken over as part of the Postal Administration at the end of the war for doing encrypted communications to troops and things of that nature. So don't be surprised if you realize that it's been around a lot longer than you assumed. Claude Shannon produced what has been described as the most influential master's thesis of all time, in which he introduced the concept of Boolean logic for relays, digital logic, and eventually becoming the foundation of digital communications, electronics, and information theory. And since the subsequent invention of the transistor in 1947, which has a strikingly material and low-tech physical appearance, has been seen has seen rapid developments in software and hardware technologies that have introduced unprecedented changes across every discipline and every industry and made digital computing ubiquitous in our everyday lives to suck us into the machine. From Ivan Sutherland's first computer-aided design tools, which would be CAD in 1963, to the first computer numerically controlled machines demonstrated by MIT's Servo Mechanism Laboratory in 1952, to the more contemporary software and fabrication platforms. This is very long-winded. We have become able to design, analyze, and physically fabricate in ways that were previously unimaginable. I'd have to agree with them up until this point. These new capabilities for computational design and fabrication have sparked a renaissance in development of materials and performance, but you haven't seen anything yet. And as we have seen, this boom in material capabilities is visible in recent developments across many disciplines. The life sciences are making rapid advancements with DNA sequencing and synthesis, genetic modification tools such as CRISPR, as well as DNA computing, microbiome research, developments in tissue engineering, and the growing field of synthetic biology. Every single one of those topics is worthy of a show. New biomaterials, synthetic biofunctionality, DNA self-assembling, drug delivery mechanisms, and bioprinting are just a few of the recent capabilities to emerge, and material science is similarly experiencing its own bustle of activity. From the discovery of graphene in 2010 to carbon nanotubules, directed self-assembly for material formation, granular jammable matter, invisibility, cloaking, and a great deal more. At the macro scale, we are also seeing similar shifts. Some of the recent large-scale advances include multi-material printing with metallic, ceramic, glass, rubber, foam, printable electronics. Really? Metal, ceramic, glass, rubber, and foam printable electronics. 4D printing to customizable smart materials. Reversible concrete-like structures with granular jamming, and even building-scale automated fabrication, printable wood, programmable carbon fiber, active textiles, and many others. Wow, this is just flooring me. And as new computational and digital fabrication processes are emerging, novel material capabilities have become available. In 2007, the Defense Advanced Research Project Agency, more affectionately known as DARPA, initiated a program called Programmable Matter. Programmable matter is generally understood as materials that have the ability to perform information processing, much like digital electronics. And the DARPA program included researchers from many universities and disciplines, many of whom are included in this book. And with a few exceptions, the researchers fell under the category of reconfigurable micro-robotics or modular robotics. Researchers developed smaller and smaller scale robotic modules with embedded electronics, powers, actuating sensors, and communication that would enable a variety of physical transformations and other behaviors. And in somewhat a traditional DARPA fashion, the program was way ahead of its time. Yeah, the vision was clear, but the implementation at the point was far from the dream of programming matter into an elegantly and seamless way. Small robots became the stand-in for matter, but they were just materials. They were accumulations of software and hardware devices. The sum was perhaps not yet more than its parts, and however, the vision of programmable matter laid the groundwork for today's active matter. Since this program, a number of developments in material science, synthetic biology, and other domains have rapidly emerged that I believe have enabled a realization of programmable matter and more. Oh, it's here, people. Now, materials can not only be programmed to compute, but they can physically transform and actively assemble into larger aggregations. These materials aren't modules that have chips or computers or batteries in them like their predecessors. These new materials are purely material. And in this sense, active matter is more than just programming matter. It is about combining programmability, transformation, and adaptation, as well as assembly. Active matter is all about matter that is literally active. One might ask, how does active matter relate to smart materials? And as an analogy, the history of computing, we have transformed the first calculators and single-function computers into today's general-purpose programmable machines. Smart materials or smart shape memory materials also have the ability to change their property in a predetermined manner. And however, active matter goes beyond today's smart materials and are only available in predetermined shapes, properties, and niche applications. Although smart materials and active matter both transform based on external input, active matter offers the freedom to design and create customized materials with unique functionalities to sense, actuate, assemble, or compute. Active matter makes it possible to make any matter a smart material. If we think about it, matter has always been active, at least at the molecular level, yet our relationship to matter has traditionally been passive, and at most we have simply guided the growth and the behavior of natural materials like bacteria, living cells, crystals, or wood. Or conversely, we have produced... Who keeps sending me messages? Stop it. Or conversely, we have produced synthetic materials, blah, 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 blah. All right, I'm going to skip over this. And we're going to go to the next level of self-adapting materials. And that would be something that is called gray goo. Eric Drexler was the first one to mention it in his book out of 1986 called The Engines of Creation. And he now regrets using that term because people use it as a fair term. But I think we should be paying attention. Gray goo is a hypothetical end-of-the-world scenario involving molecular nanotechnology in which out-of-control, self-replicating robots that are really tiny consume all of the biomass on Earth, like the ATP we were just looking at, like some of that stuff they were working on requires, while building more of themselves, a scenario that has been called ecophagy. The original idea assumed that machines were designed to have this capability, while popularizations have assumed that machines might somehow gain this capability by accident or maybe on purpose by some of the labs. Self-replicating machines of the macroscopic variety were originally described by mathematician John von Neumann and are sometimes referred to as von Neumann machines or clanking replicators. And remember, we were just reading an excerpt out of that book, and we were reading an excerpt out of a paper that Eric Drexler published in 1981, and they mentioned John von Neumann. The term gray goo was coined by nanotechnology pioneer Eric Drexler in his 1986 book, Engines of Creation, and in 2004 he stated, "I wish I had never used the term gray goo." Whoops. Well, it just gives you a good illustration. Engines of Creation mentions gray goo in 2 paragraphs and a note, while the popularized idea of gray goo was first publicized in a mass circulation magazine called Omni. Remember that one? In November of 1986. In his book, Engines of Creation, Drexler illustrates both exponential growth and inherent limits, not gray goo, but describing nanomachines that can function only if given special raw materials. Imagine such a replicator floating in a bottle of chemicals, making copies of itself. The first replicator assembles a copy of one in 1,000 seconds. 2 replicators then build 2 more in the next 1,000 seconds, and then 4 replicators build another 4 in the next 1,000 seconds. And at the end of 10 hours, there are not 36 new replicators, but there are over 68 billion, with a B, of them. And in less than a day, they would weigh a ton. And in less than 2 days, they would outweigh the Earth. And in another 4 hours, they would exceed the mass of the Sun and all of the planets combined. And if the bottle of chemicals had not run dry long before that. Oh, yeah, it's going to consume the solar system. I mean, guys, this is really nuts. According to Drexler, who was the father of nanotechnology, the term was popularized by an article from Omni magazine, which also popularized the term nanotechnology in that same issue. I read about it in Scientific American. Drexler says that arms control is a far greater issue than gray goo nanobugs. But then in a History Channel broadcast, a contrasting idea, a kind of gray goo, is referring to a futuristic doomsday scenario. In a common practice, billions of nanobots will be released into the environment to clean up an oil spill off the coast of Louisiana. Wink, that didn't happen. However, due to a programming error, the nanobots devour all of the carbon-based objects instead of just the hydrocarbons in the oil. Oh, whoops! The nanobots destroy everything, all the while replicating themselves, and within days, the entire planet is turned to dust. That's like the 21st century version of, what was the book, the radio broadcast? Didn't H.G. Wells do that, where they had read about the aliens coming to take over Earth? So anyway, Drexler describes gray goo in Chapter 11 of Engines of Creation. Early assembler-based replicators could beat the most advanced modern organisms. Plants with leaves, no more efficient than today's solar cells, could outcompete real plants. So they would be plants with leaves using solar cells made out of nanomaterials, could outcompete real plants, crowding out the biosphere with an inedible foliage. And that's a thought as well. If you remember, if they apply AI to this stuff, we found that when artificial intelligence was pitted against another artificial intelligence in a simulated environment, and they were competing for resources, whether it be food or prizes or whatever, they tended to get aggressive. Well, what is going to happen when these nanomachines have been released into our environment? They use some sort of bioavailable fuel source, whether it be ATP from cellular energy or solar energy or whatever, and they are going to be competing with biological organisms to fuel themselves. There is that rule, and right at this moment I'm forgetting it, whatever it's called, when you're faced, any organism, when it is faced with death, will do anything to try to prevent that death at the very last moment. It's called self-preservation. That is I don't know if that's a DNA type thing or whatever. It's a survival mechanism that much life replicates. So I would not put it past synthetic life. Drexler notes that the genomic growth made possible by self-replication is inherently limited by the availability of suitable raw materials. Right. When it runs out of carbon, it'll be done. Drexler uses the term gray goo not to indicate color or texture, but to emphasize the difference between superiority in terms of human values and superiority in terms of competitive success. Though the masses of uncontrolled replicators need not be gray or gooey, the term gray goo emphasizes that replicators are able to obliterate life. Might be less inspiring than a species of crabgrass. They might be superior in an evolutionary sense, but this may not make them valuable. Bill Joy, ding ding, one of the founders of Sun Microsystems, discussed some of the problems with pursuing this technology in his now famous 2000 article in Wired Magazine, which we've read a few times on this show, titled Why the Future Doesn't Need Us. And in direct response to Joy's concerns, the first quantitative technical analysis of the ecophagy scenario was published in 2000 by nanomedicine pioneer Robert Freitas. We've heard interviews by him as well. And Bill Joy was also the one that talked about Ted Kaczynski in his article in Wired Magazine called Why the Future Doesn't Need Us. If you haven't read it, definitely search that one and look it up. Drexler more recently conceded that there is no need to build anything that even resembles runaway replicators. Well, good thing now after he released that whole idea and concept to the world and DARPA went running full steam ahead into programmable matter, good thing he comes out now more recently and says, we don't need to build that. That wasn't such a good idea. This would avoid the problem entirely, he says, and in a paper in the journal Nanotechnology, he argues that self-replicating machines are needlessly complex and inefficient. In his 1992 technical book on advanced nanotechnologies called Nanosystems, Molecular Machinery, Manufacturing, and Computation, he describes a manufacturing process that is capable of a desktop-scale factory with specialized machines in fixed locations and conveyor belts to move parts from place to place. None of these measures would prevent a party from creating a weaponized gray goo were such a thing possible. Well, good. And I'm sure it is possible. Prince Charles, if you can even believe it, called upon the British Royal Society to investigate the enormous environmental and social risks of nanotechnology in a planned report leading to much media commentary on gray goo. Even CNN did a piece on it. The Royal Society's report on nanoscience was released on July 29, 2004, and declared the possibility of self-replicating machines to lie too far into the future to be of concern. Of course he did. They told him, shh, go back to sleep. More recent analyses in the paper titled Safe Exponential Manufacturing from the Institute of Physics, which was a co-writer, Eric Drexler, as well as other people, show that the dangers of gray goo is far less likely than they originally thought. However, over other long-term major risks to society and to the environment from nanotechnologies has been identified. Drexler has made a somewhat public effort to retract his gray goo hypothesis in an effort to focus the debate more on realistic threats and, get you not to pay attention to what's in our not-too-distant future with knowledge-enabled nano-terrorism and other misuses possible. In the Safe Exponential Manufacturing, which was published in 2004, it was suggested that creating manufacturing systems with the ability to self-replicate by the use of their own energy sources would not be needed, and the Foresight Institute also recommended embedding controls into molecular machines. These controls would be able to prevent anyone from purposely abusing nanotechnology, therefore avoiding the gray goo scenario. Well, phew, they have a plan. And now the ethics and the chaos. Gray goo is useful constructs for considering low probability, high impact outcomes for emerging technologies. Yeah, low probability. Make sure you keep telling us that. Thus, it is a useful tool for the ethics of technology. Daniel A. Valero applied it as a worst-case scenario thought experiment for technologies contemplating possible risks from advanced technologies, and this requiring that a decision tree or an event tree include an extremely low probability event. If such events may have an extremely negative or irreversible consequence, and I would say so, an i.e. application of the precautionary principle. Diane Irving admonishes that any error in science will have a rippling effect to the future, and Valero adapted this reference to chaos theory to emerging technologies, wherein slight permutations of initial conditions can lead to huge, unforeseen, and profoundly negative downstream effects, for which the technologists and the new technologies proponents must be held accountable. And I would second that opinion. All right, so where do we go from here? Well, I want to take a break for a second because I didn't find an appropriate place to interject for a moment. But yesterday, I received not one but two comments on YouTube that had mentioned music in one way or another. Music on a video that my channel had uploaded to YouTube. One was about my intro bumper, and one was about music filler that I'd put at the end of an interview. And I want to take a second to kind of explain to you guys one of the reasons why there is music either at the beginning or at the end of a video. There's a fast forward button, by the way, but there is a good reason for it. This network runs 24/7, and when there are new shows, whether they be live like this show or pre-recorded like a lot of the other shows, people give me weekly shows that we then cut. I put bumpers on just to keep it consistent, and then I upload. When people go live, remember there is still the issue of dealing with Skype and trying to log in and not have technical problems, and sometimes there are a bunch of live shows that all happen in a sequence, and sometimes people have guests and Skype gives them trouble. So the bumpers originally were to give the live shows the ability to get on air without having dead air. But on my back end, I have things automated and running on a schedule, so when a show goes live, when things start playing, the archiving feature starts recording, which starts at the beginning of the hour when the music starts, and it becomes part of the end result that you see on YouTube, which is all done automatically. So I don't go in and edit or cut things out or anything. So that's why the intro music is there. But you also got to realize that when people have done a show for a long enough time, like 6 years here, it becomes almost Pavlovian. I have to say, every morning I honestly don't feel like doing this some days. But it becomes Pavlovian. When I hear that music fire up, it's like the do or die moment when you're like, oh, there's no backing out now. And you have to face the piper and get yourself ready, but you get into the music. So when the music ends, you know you better start talking. So it's kind of a motivator for me, kind of like putting putting the heat to the feet to get me going. But when we put it on pre-recorded shows, it's just to kind of give it some personality and to make it consistent with everything else. And if I put it at the end of the show, that means that the hosts themselves did not provide me with a full 57 minutes of content. And so when I put it into my broadcasting and it was being archived while it was running live or whatever, real time being streamed, I needed something to fill the end of my hour. So that's what it recorded. So, okay, right turn. Now we're going to make a left turn back to where we were. So this is out of a publication called AllAboutCircus.com. This is May 1st, 2016. Is programmable matter actually coming soon? Well, there are all kinds of speculations and supposed breakthroughs in the field of programmable matter, but how close are we really? Well, whether it is the T-1000 robot from Terminator 2, the Autobots and the Decepticons, or the awesome 3D pinboard map from the X-Men movie, they are probably seen some version of programmable matter. And the term programmable matter was first coined in 1991 and has been a fascinating concept ever since. I would say actually 1981 in that paper we had read by Eric Drexler. The eventual goal is to have macroscopic machines that can rearrange their grouping and allow them to take any form of our choosing. And back in 2010, famed physicist, good old Michio Kaku, spoke about the technology's potential in his interview with Big Think. Quote, if we have a clump of clay made of 1,000 million little dots, and that's almost like that Claytronics project that Carnegie Mellon and Intel were working on, and then I push a button, then the changes rearrange themselves to form a statue, a car, or whatever you want. And that was in the demo that they had showed for that Claytronics. It was a car that came out, a car prototype. It will be a long time before we have anything that cool, but the field of self-reconfiguring modular robotics has produced some intriguing devices that could potentially be the precursor to our science fiction fantasies coming to fruition. The modular robotics breakthroughs that we do have are shape-shifting tables, 4D printed robots that can fold into different shapes, and cubes that can rearrange themselves using magnetism. And if any of these technologies or a combination of them can be scaled down successfully, we might just get to see microscopic programmable matter in our lifetime. The Tangible Media Group, as part of the MIT Media Lab, recently unveiled the latest version of Transform at the TEDx CERN conference. Transform is the form of a dynamic furniture that can turn digital information into three-dimensional shapes. It also responds to hand gestures in real time with cameras and sensors. The device consists of 900 pins that move up and down, similar to pin art toys that many of us had as children. I didn't. But thanks to Transform, we will have an awesome 3D pinboard map like the ones in the X-Files, in the X-Men and the Man of Steel. The device is currently limited by its size to its size by the pins that are able to move up and down. I could see several potential applications for this technology scaling up in size. However, imagine a changeable environment for paintball, laser tag, remote control or drone racing, or simply making mazes. And I'm sure somebody will think of more productive uses for the technology than I can, but I'm just happy to geek out over the shape-changing furniture for now. In the term 4D printing, it got me excited, and that would be the author of the story, because a lot of people, myself included, think of the fourth dimension as time. Unfortunately, 4D printing, like a 5D data disk, and I don't know what that is, does not involve time travel. It does, however, involve time lapsing. This technology is being developed, of course, by MIT's Self-Assembly Lab, yet another MIT lab that this author, neither I, had heard of until recently. And I bet you that's where they're doing that origami stuff. The concept of 4D printing is to make 3D printed objects that can change their shape over time when exposed to various stimuli like water, light, and heat, or electricity. And the idea behind the technology is to put functionality into materials without requiring a complex electronics. Currently, the main potential application being pursued by the Self-Assembly Lab is adaptive materials, and we might soon see blankets that can become rigid when they are exposed to water and then double as flotation devices. Or perhaps tents that put themselves up after being removed from their bag. We might even be lucky enough to see capes that become rigid when exposed to electrical current, like Batman someday. And although, judging by the amount of time it has taken these materials to fold themselves in MIT videos, I won't be holding my breath right away. And if the technology can be scaled down and the reaction time sped up, the potential applications for 4D printing could be near limitless. Yeah, right. Think of it on a quantum scale, guys. We can go from zeros and ones to zeros and ones simultaneously to be able to interact with flashes of light or something, and then use that 3D origami to unfold and fold themselves in different shapes on the fly. I don't know. They could do a lot of crazy things. And if you can watch these self-folding materials fold themselves with the speed increased at 75 times in the video below, you'll see what I mean. And there is a video embedded in this article, and I will include this in the notes. So self-assembling modular cubes, again, back in 2011, John Romashin, then a senior at MIT, yes, MIT again, proposed a design for a modular robot that could rearrange itself called M-Blocks. 2 years later, Romashin and a team of researchers developed a successful prototype. The M-Blocks are cubes that have no moving parts on the outside. The cubes move around using flywheels inside of them, which allows them to hop around using angular momentum. Then there are magnets on each side of the cube that allow them to stick together in various formations. And Kyle Gilpin, a member of the team that developed the M-Blocks, described how they moved in an interview with MIT's news office. Quote, there was a point in time when the cube was essentially flying through the air, and you were depending on the magnets to bring it into alignment when it lands. Romashin's team plans to upgrade these modules to be specialized to contain things such as cameras, sensors, or lights. And then the eventual goal is to have M-Blocks repairing things in hard-to-reach places, as well as quickly building structures to eliminate the need for scaffolding. They are currently working towards programming these cubes to assemble into small structures like furniture. And they also hope to scale them down in the future to a molecular level, which would have near limitless applications. So leave it all to MIT. They are compared to tiny M-Blocks to the T-1000 in Terminator 2, and much to the author's pleasure. Romashin's team has a lot of work ahead of them, mainly in perfecting algorithms for the cubes to behave autonomously to make more advanced structures, and the cube-scale M-Blocks are closer to science fiction than reality at this point, but the foundation has been laid for their arrival in the future. You can learn more about M-Blocks and watch them flip around in the video below. Since all of these technologies were developed at MIT, I would imagine that their designers have collaborated in some capacity. And now the biggest hurdle